The synthesis of alcohol is going to be the topic both of this lesson and the next. In this lesson, we're going to review some old reactions, so some substitution reactions and some alkene addition reactions that all produce alcohols. And we'll move quickly into a couple of new reactions, so the reduction of ketones and aldehydes in this lesson, and then Grignard addition to ketones and aldehydes in the next lesson, which will be some new ways for making alcohols. Now, this lesson's part of my new organic chemistry playlist. I'll be releasing these lessons weekly, so if you want to be notified every time I post a new lesson, subscribe to the channel and click the bell notification. All right, so we're going to start off by quickly reviewing some old reactions here that all produce alcohols. And so the first one's just going to be plain SN2 reaction. In this case, you got to have a good leaving group, so you got to start with an alkyl halide here. And the strong nucleophile you need to replace that leaving group with has to be hydroxide, so to make an alcohol. And so in this case, we're going to use either sodium or potassium hydroxide. And for this to be a good candidate for SN2, it's either got to be a methyl halide, which pretty much can only make methanol, or a primary halide to make a primary alcohol. So if you've got a tertiary halide, you can't do SN2. And if you've got a secondary, it actually would prefer to do E2 over SN2, so you're never going to get a good yield. So you're really limited on what you can do with this one. So this one you're pretty limited as well. So here we can consider SN1. And SN1 is not common to be used for synthesis purposes. And I'm just going to put it out there, but not a great chance you might ever even use it. So, but in this case, for SN1 to be viable here, you really need a tertiary or secondary halide. In this case, I'm using a tertiary halide, so leaving group's going to leave, forming a carbocation, and you want to replace that carbocation ultimately with a hydrox group, and water would be the reagent. So water would attack, and then we deprotonate it, subsequently leading to an alcohol. So one of the big problems with using SN1 for synthesis is you're also going to have E1 competing with this, and so you'd probably be forming alkene right alongside with this, and you can try and modulate the temperature. So at lower temperatures, this might be favored over the alkene. At higher temperatures, the alkene favored. But the truth is, you're probably going to form a fair amount of both under most conditions. So SN1 not the most common to be used for synthesis purposes, but I'm not going to rule it out completely. But again, good chance you probably never use it. All right. Then we've got some alkene addition reactions, and we'll start off with your three different hydration reactions. You guys learned acid catalyzed hydration, oxymercuration, demercuration, and hydroboration oxidation. Now, acid catalyzed hydration using either dilute sulfuric acid, sometimes just simply written as H3O+, and if you might recall, adds an H and OH Markovnikov. However, you do have to remember that it goes through a carbocation intermediate and is subject to rearrangements. And so I chose this level of reactant so that we'd see the difference between these three. And so in this case, first step, you'd add an H to the less substituted side, leaving you with a carbocation that would be secondary, but because it's right next to a tertiary carbon, it would rearrange, and that's why the OH ends up over here. So it goes through a rearrangement. Now, oxymercuration, demercuration, no carbocation intermediate, no chance for rearrangements. It just adds H and OH Markovnikov, so H to the less substituted side, OH to the more substituted side, leading to this product where the OH adds is indeed a chiral center, so you get both R and S, a pair of enantiomers there. Finally, you've got hydroboration oxidation, which adds an H and OH, but anti-Markovnikov. And so in this case, it's going to add the H to the more substituted side and the OH to the less substituted side, yielding this lovely alcohol here, no chiral centers formed. Cool. And we got a couple different ways to form vicinal diols. Vicinal meaning two hydroxyl groups on adjacent carbons, what the vicinal part means. We've got both anti-dihydroxylation and syn-dihydroxylation. Now with anti-dihydroxylation, you're going to start this. So by adding what's called a peroxy acid, you might recall, which has this generic formula, RCO3H. And the most famous example, though, is MCPBA, metachloroperoxybenzoic acid. And you're actually more likely to see it written, this specific MCPBA than a generic peroxy acid or something like that. So that's why I wrote MCPBA. So MCPBA just leads to epoxidation, forms an epoxide. But acid catalyzed ring opening of that epoxide, so forms an anti-dihydroxylation here. So two hydroxyl groups added to opposite faces of the alkene, which on a ring leads to the the transdiol from the alkene. In this case, that would be a pair of enantiomers. Now, syn-dihydroxylation carried out in two ways. We can use osmium tetroxide followed by mild oxidizing agents like NaHSO3 or Na2SO3. The hydroxyl groups add to the same face. And so in this case, whether they're both wedges or both dashes, it ends up being the same thing because this is a meso compound. Look at that plane of symmetry right there. So you could also carry this out with cold dilute KMNO4, as you might recall. So now that's the review of the old. So now let's introduce some new. We're going to talk about reduction of ketones and aldehydes. All right, before we jump into the reduction of ketones and aldehydes, I just want to go back and take a look at the reduction of alkenes as a reminder, because we'll see if we have a very analogous reaction with ketones and aldehydes. And with the reduction of an alkene, we reduce it down to an alkane, and if you recall, that adds a hydrogen to both sides of the alkene. We get additional hydrogen on this carbon and an additional hydrogen on this carbon, and it's catalytic hydrogenation here, H2 in an appropriate metal catalyst, either platinum, palladium, or nickel. Well, it turns out we can do the exact same thing with a carbon-oxygen double bond as well with catalytic hydrogenation. So when we've got a ketone or aldehyde, so this is going to do exactly the same thing. So adding an H to the carbon, but also adding an H to the other atom of the double bond, the oxygen, resulting in an alcohol. And so if we do this with a ketone, we end up with a secondary alcohol. Had we done this with an aldehyde, we would have ended up with a primary alcohol. Cool. So I just want to show that this works the same way. Now, catalytic hydrogenation, so we see is therefore not specific to alkenes or ketones and aldehydes. It'll do both, and alkynes for that matter as well. So, but it turns out we've got a way to selectively only reduce ketones and aldehydes. And so we've got another option here. We've got sodium borohydride, it turns out, in ethanol, or we've got lithium aluminum hydride, followed by what we call an acid workup step. So we've actually got three ways to pull this off. And these all three of these work equivalent, let's say, for ketones and aldehydes. The big advantage, though, is that these two here involve a little bit of a nucleophilic reaction. And so they're only going to react with a polar double bond, like a carbon-oxygen double bond. They're not going to react with the fairly nonpolar carbon-carbon double bond as a result. And so these two would be selective. So if you had both an alkene and a ketone in your molecule, well, if you want to reduce both, well, then use H2PDC. So, but if you want to reduce just the ketone but not the alkene, then you want to either use sodium borohydride or lithium aluminum hydride instead. So, cool. Now we're calling this reduction. We talked about, reduction of alkenes and alkynes. And if you reduce an alkene, you get an alkane. Now, I want to go through a little bit more and talk about what reduction actually means in this context, because with alkenes and alkynes, we just kind of took it for granted that we were reducing them. So, but let's take a look and kind of revisit what we learned in Gen Chem. In Gen Chem, you learned that with the mnemonics like oil, rig, or Leo, the line says good, you might remember that oxidation is the loss of electrons, reduction is the gain of electrons. Well, that's not the most helpful definition for organic chemistry. We can use it, and we're going to, but we'll see why it's a little easier to use a slightly different definition. So if we take a look at assigning oxidation states to an organic molecule, you want to start by drawing out their Lewis structure. So, and it turns out, rather than doing it from a formula and memorizing a set of rules for assigning oxidation states like you did in Gen Chem, we're actually going to assign each atom individually as possible. And it turns out not all the carbons in a molecule have to have the same oxidation state. You'd never see that if all you're doing is looking at the overall formula, but if you're looking at the structure, you can totally see this. And the way this works, like let's look at this from oxygen's perspective for a second. So oxygen, in this case, we normally expect oxygen to have 6 valence electrons. Well, the question is, how many does it have in this structure? So, well, for the purpose of oxidation state, the way this works, any non-bonding electrons belong to that atom. So those 4 electrons right there, those are his. So, but the shared electrons might belong to one atom or the other atom, or they might split them half and half. And the way this works, if you've got 2 different atoms, whoever's more electronegative owns all the shared electrons, specifically just for the purpose of assigning oxidation state. I realize they're shared, but in this case, we're going to assume that all 4 of these belong to oxygen, since oxygen is more electronegative than carbon. And so as a result, those 4 belong to oxygen, these 2 and these 2 belong to oxygen, and so this oxygen has the equivalent of 8 valence electrons, again for the purpose of assigning oxidation state. Well, oxygen's used to having, again, his normal valence is 6. If he's got 8, well then he's in the -2 oxidation state. That's how this works. Now I did that for oxygen because I wanted to make sure you'd seen something with lone pairs. So, but the truth is, the only atom I really care about is carbon. Carbon, he's the big one that's changing in this process as we go from a ketone to a secondary alcohol. And if we look here, this carbon right here, so those 4 electrons, again, those aren't his. Those are oxygen's. He's more electronegative. So, but when he's bonded to another carbon, that's when we're going to split them up halfway, and one of those 2 electrons belongs to him. The other one would belong to the other carbon. So there's 1 electron for that central carbon. Same thing, this is between 2 identical atoms, so we're going to split those 2 electrons up, and one of them belongs to the central carbon. The other one that's not drawn in would belong to the other carbon. And so for this central carbon right here, we figured out that for the purpose of oxidation state, he's got a total of 2 electrons. Well, carbon's normal number of valence electrons is 4. If he's only got 2, well, then he's missing 2, which means he's got a +2 oxidation state. He's in the +2 oxidation state. So that's how we define that. Now, if we look at the product here, when we convert this to a secondary alcohol, well, again, the carbon here being bonded to 2 identical atoms here, so 2 other carbons, one of those 2 electrons in both cases belongs to him. The bond between him and oxygen, those are oxygens, not his. He doesn't get any of those electrons. But carbon's more electronegative than hydrogen. And so these 2 electrons right here both belong to our carbon. And so now this carbon has 4 valence electrons, which is the normal number for carbon, and so he is in the 0 oxidation state. So if you have fewer than your normal number of valence, you're going to have some sort of positive oxidation state, and if you end up with more than your normal, you'd have some sort of negative, or if you have exactly your normal number of valence electrons, you'll be in the 0 oxidation state. And so here we can see that in carbon going from +2 to 0, in Gen Chem, we learned that that's reduction. When your oxidation state goes down, that's reduction. That's where the name comes from. And it just is evidence that you're gaining electrons. Again, reduction is the gain of electrons. Cool. Well, rather than assigning oxidation states in this kind of tedious fashion, so we come up with just some generalized rules for how you can recognize when oxidation and reduction take place. So first off, you just want to always recognize this from carbon's perspective. This is organic chemistry. You're going to be focusing on carbon. So, but when you do this then, well, when is carbon going to not own the electrons in the bonds around him? Well, when he's bonded to more electronegative atoms. He doesn't own those. When is carbon going to own the electrons? Well, if he's bonded to other carbons, he'll own half of them. So, but those bonds aren't usually changing. We're not usually adding or breaking carbon-carbon bonds in most of the reactions we're going to consider. So we'll kind of leave that out. But the only atom that commonly shows up in organic molecules that actually is less electronegative carbon is hydrogen. And so we're going to have this interplay here between carbon being bonded to more electronegative atoms or to hydrogen. That's the contrast. And so if over the course of a reaction, if he loses bonds to more electronegative atoms, like he is here, losing a bond to oxygen, and or gains bonds to hydrogen, that's going to be reduction. And these almost always happen in pairs. And so you got 3 options for a reduction to take place. You can lose 2 bonds somewhere in the molecule involving carbons, so to electronegative atoms, like losing 2 bonds to oxygens. So, or you could gain 2 bonds to hydrogen atoms somewhere in the molecule. Or you could do one of each. You could lose a bond to oxygen like we did here, and then gain a bond to a hydrogen. And that's the example we did right here. You do one of each. So, and that's reduction. Oxidation would be the exact opposite. And oxidation is the one that's a little easier to remember because oxidation sounds like oxygen, right? And that's actually where the name comes from. And in an oxidation reaction, you got one of 3 options as well, just the reverse of what we talked about. You can gain 2 new bonds to oxygen, or any electronegative atom really, anybody more electronegative than carbon, or you can lose 2 bonds to hydrogens. Or you can do one of each, like we'd be doing the reverse reaction here. We're gaining a bond to an oxygen, and we're losing a bond to a hydrogen. Those would all be oxidation. Cool. So now I've kind of given you some generalized way of recognizing oxidation and reduction, and you might be asked to do that a time or 2. Okay, so back to our reaction specifically involving sodium borohydride and lithium aluminum hydride. Let's take a look at the mechanism. All right, so you might envision, so if you look at, first of all, you got boron here, and boron's notorious for going under the octet rule and only having 6 valence electrons. I'm sorry, 6 total electrons, not valence, but 6 total. So as a result, in this case, you'll notice that that's not, usual for boron. Boron actually has a filled octet here, but that's going to leave him with a negative formal charge. So boron in this case, though, he's perfectly content as far as atoms go anyways. If anybody's got to do it, pick boron for only having 6 total electrons around him, not the normal filled octet. And so in this case, picture one of these hydrogens breaking off. So picture that breaking off. What that would leave you with is a boron that is still bonded to 3 hydrogens, but also with a hydride ion, a hydrogen with a negative charge. So that's not H+, that's H-. And this hydride ion is both a strong base and a strong nucleophile. And so then you could picture this strong nucleophile here. That's where this hydrogen actually comes from. He's a strong nucleophile, and he's like, oh, look at that carbon right there. That carbon-oxygen bond is really polar, and that carbon has a significant amount of partial positive charge, and this hydrogen's negative. Okay. So the electron-rich hydride ion is going to come and attack, i.e. attach to, the electron poor partially positive carbon there. And so it turns out ketones and aldehydes are good electrophiles. Now, this carbon up here, though, that we're attaching to already had a filled octet. So if we're going to attach to him a fifth bond, well, that's not going to happen. So what has to happen then, if we're going to attach a bond, simultaneously one of the old ones has to break. And that's this bond right here. The double bond to oxygen is going to go away, and the pi electrons are pushed up onto the electronegative oxygen, which is why we end up with a carbon-oxygen single bond. And so in this case, we're going to end up with this guy, and we don't normally draw the hydrogen in, but I'll draw him in. There's the hydrogen that just attached to this carbon. Again, we don't normally draw hydrogens that are bonded to carbons unless it's an aldehyde, and this is not. So we form this alkoxide initially, and then this oxygen needs to get protonated, and that's just going to happen from our solvent, the ethanol here. So that's what that protic solvent's purpose is in this reaction, or at least one of them. And that gets us to our secondary alcohol. Again, this other hydrogen we wouldn't draw in normally, but it is still there. And so we've added a hydrogen to the carbon, we've added a hydrogen to the oxygen, and there's our final product of this reduction reaction. And again, if you do this with a ketone, you get a secondary alcohol. If we did this with an aldehyde, we'd get a primary alcohol. Cool, so this is how this works with sodium borohydride. So, except it isn't, not quite. So it turns out this doesn't actually happen in two separate steps. This hydride ion doesn't break off and then form, one break off and then form a hydride and then go and attack. So it turns out it all happens in a single step. And so rather than having this hydride that broke off attack, what happens is instead of having this break off and then attack, it breaks off from boron and attacks at exactly the same time. That's how it works. So this is, this bond right here is a little bit polar and stuff like that, but it's actually not going to dissociate and then attack. It's just not favorable. But it will dissociate to attack at the same time. Cool, so this never actually dissociates. We never actually form BH3 and H- and stuff like this, and that's a good thing. So it turns out this works a little better. So this is less reactive than having H-. We could use something like sodium hydride or something, but it turns out it's not going to do ultimately exactly what we want if we use sodium hydride. This is kind of a hydride. They call these hydride reagents, sodium borohydride. But for the purpose of what we're using here, it works significantly better than sodium hydride because we got some other competing reactions that would happen if we use sodium hydride. Now, in addition to borohydride here, we could also use lithium aluminum hydride. As well. And so instead of the central atom being boron, the central atom's aluminum. Now, the difference in electronegativity between boron and hydrogen is not as big as the difference between hydrogen and aluminum. And so as a result, this is a more polar bond right here. And being a more polar bond, this hydrogen has a more significant amount of partial negative charge than he did when bonded to boron. And having a more significant amount of partial negative charge, this is a little bit closer to having that free H- ion. Now again, we don't have a free H- ion, and it doesn't break off and then go and attack. It does it all simultaneously here as well. So if we were using lithium aluminum hydride, then he would come and attack again, break off and attack all simultaneously. But it turns out with lithium aluminum hydride, it's more reactive, being, again, we have more partial negative charge in that more polar aluminum hydrogen bond. Now, this has a couple of major consequences here. All right, so we got lithium aluminum hydride, sometimes abbreviated LAH. You should be prepared to see it that way. So, but problem is I can't just do like we did before here. I can't just be like, oh yeah, just put it in ethanol. Life is good. So, because it's not going to work. Lithium aluminum hydride is more reactive and is both a stronger base and a stronger nucleophile than sodium borohydride. And it turns out if you put lithium aluminum hydride in anything protic like ethanol, it'll just simply deprotonate that H. And so one of the H- breaks off and comes and grabs an H+, forming H2 gas, which bubbles out of the solution. And you never get a chance for one of these H's to actually attach to your ketone. And so it turns out lithium aluminum hydride is not compatible with protic solvents. It's too strong of a base to ever put in a protic solvent. So you can't mix lithium aluminum hydride with water or an alcohol. And so putting this in ethanol like we did with sodium borohydride, not going to work. And so it turns out we've got to carry this out over the course of two steps. We'll use lithium aluminum hydride in an aprotic solvent, and nobody ever takes the time to show you what that aprotic solvent is, but it's usually like an ether or something like that. So, but don't have to list it, just put lithium aluminum hydride. So, and using lithium aluminum hydride, actually, I'll just leave that alone, would get you this far. It would get you to the alkoxide. So, but because you don't have a protic solvent, you have no way to protonate the oxygen to finally get your alcohol. And so what you actually have to do is a separate acid workup, we say, where you add some H3O plus in a separate step. Cool. Now you can actually use this kind of sequence of steps with sodium borohydride. You could use sodium borohydride in an aprotic solvent followed by H3O plus. You could do it that way. You just don't have to. And you more commonly see it presented this way, where we just use sodium borohydride in a protic solvent like ethanol. Cool. So, but we got two new ways now to reduce ketones and aldehydes. And again, these are selective for ketones and aldehydes. They will not react with an alkene. Now you'll find out later on, we'll learn some other functional groups later in the semester that also have a carbon oxygen double bond, like carboxylic acids and esters and stuff like that. And you'll find out that there's some other reactions that these might do, and you'll find out with lithium aluminum hydride being more reactive, it reacts with more stuff. So you'll find out like if you wanted to reduce a carboxylic acid or an ester or an amide, you'd have to use lithium aluminum hydride. Sodium borohydride wouldn't work. But I'm alluding to that now. I'm not teaching it to you now. We will talk about that much later in the semester. All right, so in this lesson, sum it up here, we learned that with lithium aluminum hydride or sodium borohydride, we have the equivalent of H minus. We have a polar bond that leaves hydrogen with a partial negative charge, and it acts as if it's a hydrogen anion, a hydride ion. Well, in the next reaction, dealing with what we call Grignard reagents, we're going to have a polar bond involving carbon, where carbon has a partially negative charge and acts as if it's a carbanion. And so instead of attaching a hydrogen to that carbon, we'll have the ability to attach a carbon chain. And that's going to be super important because, again, very few ways we have of making carbon-carbon bonds, and we're about to learn a new one, and it'll be a very important one from the standpoint of synthesis. Now, if you found this lesson helpful, would you consider giving me a like and a share? A couple of the more helpful things you can do to help support the channel. If you've got questions, feel free to leave them in the comment section below. If you want the study guide that goes with this lesson, if you're looking for practice problems, check out my premium course on chadsprep.com.